Good morning, students. So, today in this class, we are going to discuss the Module 1 first topic, that is BGT biasing. So, in BGT biasing, we are going to study two different biasings. That is, one is a classical discrete circuit bias, but it's also known as voltage divider bias. And the next one is biasing using a collector to base feedback resistor. Next chapter is small signal operation and models of the BJT. Here various topics it has been included. And the next chapter related to the MOSFET. Again we are studying various biasing schemes and then small signal operation and modeling of the MOSFET. So today we are going to just see the classical discrete circuit bias, that is voltage divider bias. Okay, so now biasing in BJT amplifier circuits. So biasing to BJT, which means that establishing a desired value of VCE. That is, VCE means collector to emitter voltage or output voltage, and collector current IC. That is to ensure that amplifier will have the proper gain and input impedance with undistorted output voltage swing. Okay, so here the amplifier, when we are telling, amplifier will be used to obtain the gain and proper gain and input impedance with the undistorted output voltage swing. So how we can achieve all these requirements is, that is by establishing the desired values of VCE and IC. So these values of VCE and IC are together known as the quiescent operating point or Q point, or it is also known as DC bias point. Now the basic problem with this transistor is establishing and maintaining the proper values of this VCE and IC at the quiescent point. So these quiescent VCE and IC refers to the values under the DC conditions. So I'm specifying this under DC conditions in absence of any AC input signal. Means, and in the absence of AC input signal, we are providing some DC conditions. That is, we are setting our transistor to operate in the active region. Okay, so that is nothing but the quiescent values. So these quiescent values of voltages and currents are maintained by using the configurations that assure the stability against the variation in the temperature. Finally, what we are going to obtain from the circuit is stable output. Okay, so stable output means how much stable is your circuit if there is any variation in the temperature or any other parameters. Variation in the temperature which affects the several critical transistor parameters such as ICO, that is reverse saturation current, which will also affect the base emitter voltage in the active region, that is VBE, and the current gain beta. So whatever the biasing I am telling here, so what I can give the definition for biasing is, these are the DC currents and voltages in the circuit which are established by using the resistor network along with the power supply. The process is known as biasing. So these are nothing but DC currents and voltages at the various points of the circuit which are established by using the resistor network along with the power supply. It might be a single power supply or dual power supply. Next, the biasing problem. Yeah, the main thing we can observe here is, that is why we require biasing. That I told already, that is to make the Q point, that is bias point, DC bias point on the center of the load line to get the faithful reproduction of the output. So that is why we go for the biasing. So if the DC point, bias point, if it is at the center of the DC load line, we are going to get the maximum output signal swing. Now when we are going to bias the circuit, various problems we are going to face. So what are those problems? The first one is, we need to achieve constant current. We need to establish a constant DC current in the collector of the BJT. Means collector current. We should maintain a constant collector current, and then whatever the collector current we are going to establish, it should be a calculatable one, it should be a predictable one, or it should be insensitive. This is very important. It should be insensitive to variation in temperature and to the large variations of the beta. Okay, so that is what one of the problem. And the next problem is, another important consideration in the bias design is locating the DC point in the IC-VCE plane. That is to allow the maximum output signal swing. So if we get the DC bias point at the center of the DC load line, so I am telling at the center of the DC load line, then we are going to get the maximum output signal swing. This is one of the consideration. And the next consideration is biasing the BJT by fixing the VBE. That is, fixing the VBE is nothing but fixing the base voltage. That is by using the voltage divider across the supply. That is VCC. So even though by making use of this voltage divider, even though if it affects the VBE, small change in this VBE does not affect your output much. Okay, and the last consideration is the IB, that is a base current. It should be maintained constant. If VB is constant, even IB is also constant. So what happens if you take an example? Same transistor, going to take, suppose one circuit is there. So a circuit consists of 5 to 10 transistor. Same transistor I am going to make use of PNP transistor, let us say. So each PNP transistor, which will be having various beta values, this beta value depending upon the manufacturing process. So it did not be same. Beta values will be same for this 5 to 10 transistors. So because of this beta variation, your IB should be maintained constant. Okay, so that we are going to get, that is by doing the proper biasing. So biasing a transistor is very important. Even though if we face many problems, we are going to find a solution to we are finding. I'm sorry, very sorry. So even though if we are facing so many problems, how to come out of this problem is also very important. So that is why various schemes, biasing schemes, it has been introduced. So one of the very good approach we are going to see today, that is classical discrete circuit biasing. Okay. So need for biasing, as I told, transistor means the output signal power will be larger than the input signal power. So that we are going to get biasing the transistor. So biasing the transistor, that is to operate transistor in the desired region. Two purposes are there. One is to operate the transistor in desired region and to get the output signal power greater than the input signal power. Next is, before going to discuss about the good schemes, biasing schemes, let us see what are the available schemes which is not a approachable one. Okay, so two schemes it has been discussed over here. Many schemes are there. Now, first one you see, first figure, this is a biasing scheme by fixing the VB. Okay, that is by fixing the VB. One of the four consideration, that is fixing the VB. For instance, this is being done using the voltage divider. Okay, and the power supply is being provided for that network. So, why this is not a viable approach is, there is a very sharp exponential relationship between IC and VBE. Okay, IC and VBE means that any small and inevitable differences in VBE from the desired value will result in a large variation in IC and in VCE. So it affects the output more. That is why this is not a viable approach. And the second approach is, that is by fixing the base current IB. Fixing the constant current IB. So even this is not a recommended approach. Why? Because typical large variations of beta, it will affect your IB. So that will affect your large variations in IC and hence in VCE. Even this is not also a viable approach. It is not a recommended approach. So the next good scheme, biasing scheme, is classical discrete circuit biasing arrangement. Okay, so so here the most commonly used arrangement for biasing is discrete circuit transistor amplifier if only a single power supply is available. So here we are going to make use of a single power supply, that is VCC. So this technique, it consists of supplying a base of the transistor with a fraction of supply voltage VCC through the voltage divider R1 and R2. And this resistor RE, it is connected to the emitter in addition. So this resistor RE, it is connected, it is acting as a negative feedback resistor. I'll tell you what is the importance of this resistor RE later. So next is, so here the point is, now we need to obtain the base voltage as constant. If VB is constant, IB will remain constant. So how to obtain this VB as constant? That is by fixing the VBE. How to get the constant VB? That is from the voltage divider network R1 and R2. So we need to design the circuit such that R1 and R2 it should be a fixed one. From this we will be getting VB as the fixed one. VB as the fixed one. So by fixing VB, even though if there is a small variation in VBE, that does not affect the output. IC will be a fixed one. IC will be a fixed one. Now, see how to obtain the base voltage, that is by applying the voltage divider rule over here, or else obtain the Thevenin's equivalent of the potential divider network. If you obtain the Thevenin's equivalent, VTH, Thevenin's equivalent voltage will be voltage divider rule. That is voltage VBB is nothing but voltage across the resistor R2, which is nothing but VCC into R2 divided by R1 plus R2. Next is equivalent resistance, Thevenin's equivalent resistance. RB is nothing but R1 parallel to R2, or R1 R2 divided by R1 plus R2. When I say the design of classical discrete circuit bias arrangement, we need to calculate R1 value, R2 value, RE value, RC value, IB, IC, IE. So here we are going to maintain VB as constant. If VB is constant, IB is constant. IB is constant means your IC will remain constant and IE will remain constant. Thereafter, VC will remain constant. That is what actually we want. That is a stable output. Next is, this is regarding the Thevenin's equivalent. You can refer this. See here, calculating the resistance here, equivalent resistance, Thevenin's resistance and Thevenin's voltage. So while calculating the resistance, we need to consider VCC as a short circuit here, and here we need to consider VCC. Voltage across the resistor R2 is nothing but the Thevenin's voltage or as bias voltage VBB. So this is RB and this is VBB. Okay, so the next thing is we need to calculate what is the amount of base current, what is the amount of collector current, and what is the amount of emitter current flowing, and what is the output voltage VCE. This we will be getting by applying the Kirchhoff's voltage law at the input side and at the output side. So here VTH, that is Thevenin, apply the Kirchhoff's law for the input loop, that is base emitter loop. So it will be VTH minus IB into RB. This is nothing but RB. So VTH is VB, bias voltage. So VB minus IB RB minus VBE minus IE RE. And then we know IC plus IB is equals to IE and IC is equal to beta times IB. So when you substitute beta IB in this equation, you will be getting in terms of IB only here, left hand side. So take IB outside, you will be getting IE as beta plus 1 into IB. Now you substitute this IE value in this equation, so you will be getting in terms of IB here, this in terms of IB, and this term is also in terms of IB. So IB is common, so you can obtain the equation for IB as, rearrange this, VTH minus VB divided by RTH plus beta plus 1 into RE. Similarly, you can obtain the expression for IE. Here, wherever IB is there, substitute IB in terms of IE. So what is that? IB is equals to IE divided by beta plus 1 into beta plus 1. Substitute in this equation, fourth equation. So at that time, you will be getting the equation for IE. See, IB as IE by beta plus 1. Now the equation 4 will become VTH is equals to RTH IB I substituted it as IE by beta plus 1 plus VBE plus IERE, then VTH minus VBE to the other side. Then here IE is common, take that outside, inside the bracket you will be getting this. So IE can be written as VTH minus VBE divided by RE plus RTH plus beta plus 1. Okay, so here VTH, this will be constant, VBE will be very much less, that won't affect your emitter current. Okay. Next is getting the equation for VC. So here VC is equals to output applying KVL for the output loop, VCC minus ICRC minus VCE minus IER. So VC can be written like this because IC, wherever IE is there we are substituting it as IC because IC is nearly equals to IE. Then you should know these expression also, that is VE can be calculated as IE into RE. VC is nothing but VC plus VE and VB is nothing but VB plus VE. Okay, you need to know this expression from the problem solving point of view. So remember these equations. Next thing is, see here, from the emitter current equation. Emitter current equation, so emitter current equation. Now here in the circuit, what we need to observe here is, whatever the current we are getting, that is IE current, whether it is constant even during the saturation condition also. So to make, so when this IE will vary, if there is a variation in the temperature and beta. So what we need to make here is, we need to make IE insensitive to temperature and beta. Means as the temperature increases, it should not affect your IE. If there is any large variation in beta, that should not affect your IE. Okay, so make IE is insensitive to temperature and beta. So we design the circuit such that to satisfy two following constraints. So in order to make IE insensitive, two constraints are there. What are those two constraints? That is, one is we should make VBB, that is the bias voltage, greater than the, or base voltage greater than VBE, base to emitter voltage. Of course, it will be, this VBE will be very much less than VBB, but what amount, high amount of VBB can be applied, that we need to know. So that is given over here. So the condition 14 ensures that small variation in VBB will be swamped by the larger VBB. So larger the VBB if we take, this will be avoided. Changes in the VBE can be avoided. But there is a limit for VBBs. However, on how large VBB can be applied, this is a question. So for a given value, let us take an example. For a given value, the supply voltage VCC, so VBB will be derived from VCC. Correct? No? So VBB will be getting from this potential divider network, that is derived from VCC. So for this given supply voltage, the higher the value of VBB, the lower the value of, lower will be the voltage across RC and this one. See, what they are telling is, VBB is nothing but voltage across R2. If voltage across R2 is greater than this R1 means that voltage across R1 is less. Voltage across R1 is nothing but, this is nothing but, this is equals to this, that is voltage across RC and voltage of collector to base, VRC plus VCB. So if this is greater than this one, this will be less. If this is less, voltage across RC is less and voltage of collector to base is also less. But to obtain the proper gain, higher gain, the voltage across RC should be larger. So we need to choose such that VRC, voltage across RC is sufficiently, it is large enough to obtain the proper gain. So this is what we maintain. So for that, so if the voltage across RC is more, means we are going to obtain the maximum voltage swing, output voltage swing. So for that, there must be a trade-off. Solution is, there must be a trade-off. What is that trade-off? VBB. that is the base voltage. All these are derived from VCC only, right? So VBB must be 1/3 of VCC, and collector to base, it is going to reduce, no? These two is going to reduce if I increase VBB. So what we are doing is we are making VBB VCC by 3 and VCB also VCC by 3 and voltage across RC also VCC by 3. So all these are derived from the VCC. It has been equally divided. So we are going to maintain all these voltages as equal. So there won't be any reduction in the voltage across RC or voltage across VCB. All the voltages are equal. This is how we are going to maintain the first constraint, VBB greater than VBE. And the second constraint is RE should be greater than RB by beta. See, beta value will be very much large. From this expression itself, we can identify that your RE value, it will be greater than RB, because beta is greater means the entire this factor will be less, right? Because this is in the denominator, so this will be less, right? So RE will be greater than RB, of course, RB by beta plus 1. Beta plus 1. So lower the okay. So condition 15 makes IE insensitive to variation in beta and could be satisfied by selecting RB as small. So we need to select here RB as small. RB as small means it indicates that we need to select R1 and R2 as small. So how we are going to make this R1 and R2 as small? There is a condition for that. That is, whatever the current flowing in the potential divider network, that should be within the range of your emitter current. That range is from IE to 0.1 IE. So IE to 0.1 IE. So there is a range for emitter current. So potential divider current must be less than your emitter current range. Emitter current range is IE to 0.1 I. Okay, that is what it has been given here. Typically, one selects R1 and R2 such that their current, potential divider current, is in the range of IE to 0.1 IE. So consider that for some reason the emitter current increases. If the emitter current increases, the drop across RE, and hence VE will increase accordingly. So now, if the base voltage is determined primarily by the voltage divider R1 and R2, which is the case if RB is small, it will remain constant and it will increase VE, which will result in corresponding decrease in VBE. This in turn reduces the collector current, a change opposite to that originally assumed. So thus RE provides a negative feedback action that stabilizes the bias current. So this should remind the reader of the resistance RE. Means RE is acting as a negative feedback resistor here. Why? Because if there is any changes in the VBE occurs, that will affect your output. Output may increase. Suppose sometimes output increases means this RE, by varying the values of RE, we can obtain the proper output. Stable output we are going to obtain. So this is why the feedback resistor is given. So this is the explanation for your classical discrete circuit biasing. I hope it is understood. So if you go to the advantages, it provides excellent stabilization against the variation in temperature and transistor current gain. And disadvantages when you take the negative feedback, which reduces the gain. So however, this problem can be solved by reducing the capacitor in parallel with RE. So how the gain reduces? Because if you apply the Kirchhoff's law at the output load, even IE RE drop is also considered. If this is large, then the gain will be less. So that is why by providing a capacitor, by including a capacitor parallel to this resistor, what happens? This capacitor will be acting as a short circuit for the AC input and makes AC feedback equal to 0. This is what we can do. So this is one of the disadvantage. I hope it is understood. So next class we shall discuss on the problems of the uh, classical discrete circuit biasing. So when they ask, you may expect this question for 8 marks. So when they ask, very important concept it is, these two circuits you need to draw, and how did you obtain this two values? It is been given in the next slide. You can write this, and then you need to obtain the various equations IB, IE, VCE equations. It is given here. You need to write that, and then you need to explain these two constraints, how it is maintained. That is, one is rule of thumb rule, and next one is typical range of a IE, potential divider current, that is within the range of IE to 0.1 IE, and then advantages, disadvantages you can give. Okay, thank you. See you in the next session.